Okay, good morning. Let me start with a note. Last time we have done the classical ideal gas problem, and we have found the following. Here's our entropy expression. That's what we have calculated. NKV Here is our heat capacity result. Do you see any problems with this? Can you tell me if these results are okay, or do we have any problems associated with them? Any problems? Anybody? You don't see any problems with this, but there is a problem. According to third law of thermodynamics, both of these have to go to zero as temperature goes to zero. That's the third law of thermodynamics, isn't it? There's a problem, none of them goes to zero. As temperature goes to zero. And it is required by the third law of thermodynamics, but both of them should go to zero. What is the reason? Can you give me any reason for this result? The reason is that you are replacing the sum with an integral, and this integral replacement is not justified near temperature 0 Kelvin. Not justified. The reason here is that the ground state at that limit, since ground state becomes important, but there's no contribution from p equals 0 to the integral. So that's the problem. In classical approximation, we have a problem. Now, there's also one more thing I want to underline before closing the ideal gas problem, and it is the condition where the classical approach is appropriate. You have to know that. When is it applicable? Do we have any questions with this? Understandable, I hope. Now let's look at the condition where what is the meaning of classical approximation in certain special terms, physical quantities, in other words. Now, let's look at the probability of occupation of a single state. Well, you can write this as e to the minus beta ER, probability of finding the particle in a state with energy UR. It is canonical distribution, so that's our probability, isn't it? Now, what is the mean number of particles in state R the mean number, average number of particles, total number times this probability, isn't it? So let's look at this. The condition for classical regime well, we want this number to be very small for classical regime to apply. And this is for all the states R. If that is the case, we are in the classical regime. Now let's look at this condition and see what is the meaning of this. Well, looking at the expression for PR, we can write this average number of particles in a state R as total number of particles divided by V, 2 pi mkBT over h squared, 3 hours e to the minus beta ER. And we want this to be very small. That's the classical regime. This holds if this multiplier is smaller than 1, n over v. Well, this 1 over that quantity, you can rewrite that as h squared over 2 pi mkBT. 3 hours must be small. The quantity in the parentheses, can you tell me what it is? I told you this before. I asked the same question before. What is the unit of this? Square root, h squared is h, divided by square root 2 pi mkBT. Well, apart from 2 pi m, kBT is the thermal energy. So h square root of energy, what is this? It is like a wavelength, isn't it? We call that thermal wavelength. It's like de Broglie wavelength, h over p. The result is p, isn't it? H over p. So let's write that as, well, lambda t cube. Now, that thing goes down as V over N. V over N is volume per particle. So if you write as a distance cubed at volume per particle, this A is like distance between particles, average distance between particles. So you are really comparing two distances. That is also equivalent to lambda t is very much smaller than A. Extremely important. Again, lambda t here is thermal wavelength, square root of h squared 2 pi mkbt. This is so the condition can be restated as the thermal wavelength to be very much smaller than the interparticle distance. A, you can look at A as interparticle distance. So we have a condition for the quantum effects to be important, and it is that the thermal wavelength becoming comparable to interparticle distance. We are going to see this in the quantum gases like fermions and bosons. For example, when the interparticle distance and the thermal wavelength more or less equal to each other, you can see the start of Bose-Einstein condensation in a Bose gas. Okay? When the number of particles is constant. We are going to see this. So that is an important quantity. You have to understand thermal wavelength. And you should also understand clearly that the kBT is nothing but thermal energy corresponding to a specific temperature. Okay? That's the condition. So always check thermal wavelength and compare it with interparticle distance, and you can say about the classical quantum limits. Now, let me give you another example. I will continue with examples. Harmonic oscillators, before I go to the quantum mechanical examples for the canonical ensemble. Do you have any questions up to now? Okay. Let's go to the oscillator problem. We have done it in microcanonical ensemble. Let's see what we are going to get if we solve the same problem within canonical ensemble. This is example number 2. I will consider a system of harmonic oscillators and independent harmonic oscillators. So, example again. as I have done for the microcanonical ensemble. I will do this second one. Harmonic oscillators. Let me solve the problem in the classical case. Okay. We can solve the same in quantum. I will do that too. So let's do this. So we have a set of examples or problems at hand where we apply our major theory. The Hamiltonian for this is for the ith one, that is the 1/2 k q squared term. The other one is the kinetic energy, and we have n oscillators. So I goes from 1 to n. Now let's calculate, by using this Hamiltonian, single oscillator partition function. Single oscillator partition function, canonical partition function. That would be, well, since we have now Q and P, we have double integral from minus infinity to plus infinity. So that means I'm doing this in 1 dimension, if you like. 3 dimensions is just going to be multiplied by 3. So the exponential then, well, that is the sum turned into integral, isn't it? Exponential term is minus beta times the Hamiltonian. Since I have 1 dimension, it's dq dp divided by h. Now we have to discuss this factor, and we have to relate this to the density of states. To turn a sum into an integral, you need the density of states. Have you seen this in undergraduate course? Probably yes. Okay. So, the result is quite simple. These are Gaussians, okay? Q squared term and P squared term. We know that integral. So the result is to be written immediately as 2 pi beta m omega squared 1/2 times 2 pi m divided by beta 1/2. Remember, from minus infinity to plus infinity, e to the minus alpha x squared is square root pi over alpha, isn't it? So that's the result. Omega squared term is coming from Q integral. The other term is coming from P integral. So let's go to N oscillators. Well, oscillators in physics usually are distinguishable. They are sitting at certain lattice points, for example, and vibrating. Huh? So, because of the fixed positions, we can distinguish each of them. So, distinguishable was what? Qn as a function of temperature is just one oscillator partition function raised to the power n. If indistinguishable, we have to divide it by n factorial, as we have learned in the last lecture. So the result will be, since this is equal to 1 over beta h power omega, or kBt over h power omega, it is kBt over h bar omega to the power n. Well, another reason why they are distinguishable, we are dealing with energy levels, not particles. So we can distinguish energy levels, can't we? Huh? Ground state, first excited, second excited, etc. Okay, let's continue with the thermodynamics. If we know the partition function, we know everything. Let's do that. Here is the Helmholtz free energy. Minus kBt ln of Qn. Very simply, n comes down from the power n. So it becomes nkBt. I can get rid of this minus sign by turning the quotient there. So kBt comes down. ln h bar omega over kBt. See, I have an explicit expression for Helmholtz free energy. So I can calculate, for example, the chemical potential. Very easy. Derivative with n, just it's a multiplier, you lose it. kBt ln h bar omega over kBt. Pressure, we are not going to get anything, they are just vibrating. So pressure is minus del A del V, keeping N and T constant, and it is 0. Helmholtz free energy does not depend on volume. Let's calculate the other quantities. Entropy, for example. Well, let me leave it for you so you can do the derivatives very easily. You should do something. Minus del A del T, keeping N and V constant, gives you nkB ln kBt over h bar omega plus 1. Internal energy comes out to be derivative with respect to beta ln Qn beta, that comes out to be nkBt. You have to check these results. Enthalpy comes out to be equal to internal energy, because enthalpy is U plus PV, but P is 0, so that is equal to U. This means heat capacities must be equal. CV must be equal to Cp. They are equal to NkV. Okay. These classical results are in line with the equipartition theorem. So, and these results are exactly equal to the results we have earlier. Now let's check the quantum case. Same problem in quantum case. Let's see what we are going to find. That must correct some of the mistakes we are finding. Is entropy going to 0 when temperature goes to 0? Huh? It is not, isn't it? Let's do the same problem in quantum. You probably have done this before, but just reminding you what you have done. In the quantum case, the energy levels of a one-dimensional harmonic oscillator can be written as n plus 1/2 h bar omega, where the quantum number goes from 0, 1 to integers values. So we have what? Equidistant energy levels, aren't we? Now, the calculation of single particle or single oscillator partition function is quite straightforward in this case. Well, in the quantum case, since energy levels are discrete, we can sum over them to get the partition function, and it is e to the minus beta En, and that is there's a term that doesn't depend on n, 1/2 term. We can take it out of the summation sign, so it is minus beta h bar omega over 2 sum over n. e to the minus beta h bar omega. This n in the exponent is like taking to the power n, isn't it? So this is like a power series, and we know how to sum it. What is the result? X to the n is 1 over 1 minus x. Can you do it yourself? Can you see it? Yeah. Multiply the sum by x, you get the rest of the sum without the 1. 1 minus x comes from there. So the result is the constant term times 1 over 1 minus x. X is minus beta h bar omega. So you can simplify if you like by taking into help of this parentheses. You can simplify and get the following result. Isn't it? What is this? Denominator is sinus hyperbolic, isn't it? Twice the sinus hyperbolic. So it is 1 over twice the sinus hyperbolic, or 2 sinus hyperbolic, beta h bar omega over 2 to the power minus 1. Very simple result, and I'm sure you have done this before, but you have to check, you have to do the calculations yourself, so you have a feeling of what's coming up in the exams. The n oscillator partition function, just raise this to the power n, so Q1 beta to the power n, and that is 2 sinus hyperbolic beta h bar omega over 2 to the power minus n. Now you can get the thermodynamics starting from Helmholtz free energy, because you know the total partition function. Let's do that. Very pedagogical thing to do. Minus kBt ln qn beta. That comes out to be n kBt ln 2 sinus hyperbolic beta h bar omega over 2. Minus n cancels the minus in the expression, so that's it. You can rewrite, if you like, using the explicit exponential minus exponential minus, the definition of sinus hyperbolic, in the form, why don't you play with this? Ln 1 minus e to the minus beta h bar omega. Pressure is also 0 in the quantum case. I don't have to do it. Nothing depends on volume. Let's look at the chemical potential and the entropy. Mu comes out to be A over N, and it is H bar omega over 2 plus KBT ln Why is this? Because mu gives free energy per particle, G over N, but P is 0, so G turns into A. Okay. Entropy. This is what we have to calculate seriously. And that turns out to be, you have to do the calculation. I recommend this. NKB 1/2 beta H bar omega cotangent hyperbolic beta H bar omega over 2 minus ln 2 sinus hyperbolic beta H bar omega over 2. Or using the equivalent expression, you can rewrite as beta H bar omega e to the beta H bar omega minus 1 minus ln 1 minus e to the minus beta H bar omega. Now you have to look at the low temperature limit, and in low temperatures this becomes exponentially small as required by the third law of thermodynamics. So quantum mechanics fixes the problem in classical approximation. Now let's see what are we going to get for the internal energy and heat capacities, and there we should check whether the quantum oscillators obey the equipartition theorem. That's what we should ask ourselves. And the result is as follows. U, the internal energy, comes out to be why don't you check this? You should go through everything I'm writing. That's the internal energy. And since pressure is 0, U and enthalpy, internal energy and enthalpy, are equal. Cp and Cv must be equal. And it becomes something like this. NKB beta h bar omega squared e to the beta h bar omega minus 1 squared. So what is the verdict in this case? Do they obey the classical equipartition theorem? We don't have any multiple of 1/2 to kBt, isn't it? So they don't obey the partition theorem since this is the quantum case. Quantum oscillators do not obey the classical equipartition theorem. Now, can we get the classical result from this? That's another question we should ask ourselves. Can we check the classical limit? When do we have the classical limit? Always high temperatures, aren't they? The limits should not be forgotten. Classical limit is the high temperature limit. Low temperatures make it the quantum case. Why? Well, thermal wavelength is inversely proportional to temperature, isn't it? Square root h squared over kBt. It goes like 1 over t. So t is small. When it becomes small, lambda t becomes larger. So it approaches the interparticle distance. Remember? So low temperatures are quantum limit. High temperatures are the classical limit. You should always think about the quantities defined in physics. We never define useless quantities. So let's check the high T classical limit. What happens to beta h bar omega? Well, it is h bar omega over kBt. It becomes very small, isn't it? At high temperatures, inversely proportional to temperature. T is very large compared to energy level spacing. So that's the classical case. So the internal energy turns out to be, well, in this limit, 1/2. Well, it was 1 e to the beta h bar omega minus 1. So in this case, when beta h bar omega is very small, we can expand the exponential and write this as 1/2 plus 1 over 1 plus beta h bar omega, other terms, minus 1. If beta h bar omega is small, its square is even much smaller, isn't it? So you can stop at the first correction. So they cancel. And 1/2 is going to be small simply because you are dividing 1 by a very small quantity. It's a very large number. So the result is n h bar omega 1 over beta h bar omega. H bar omega cancels. We have n kBt. That is the classical result, isn't it? Okay. Now we have done both classical and quantum harmonic oscillator problem. It's a nice point to stop. After the break, I will continue with the canonical ensemble. I will try to tell you a little bit more. My main aim in the next lecture will be energy fluctuations and paramagnetism. Okay?